everyone, welcome to Chapter 9. This one is on single factor ANOVAs. I wonder what gave that away. But anyways, in case you're wondering what ANOVA stands for, it is analysis of variance. And the fact that we're looking at a single factor means we're looking at just one independent variable. And if we scoot down here, the 3 or more means that we have 3 or more levels of our independent variable, which means we have 3 or more means that we want to compare. And this analysis is appropriate in that situation. You would not want to use t-tests if you have 3 or more means to compare. And we are going to lead into that discussion in just a second. So just to give you a little bit of a heads up, we're going to talk about why you shouldn't use t-tests to compare 3 or more means. And then we're going to talk about some general information about ANOVAs, and we're going to look at the F value, which is calculated for every ANOVA. Your test statistic is an F value. And then we're going to conclude with the one-way independent ANOVA and the one-way repeated ANOVA. Now, we're not going to get to the very end, in this first lecture. But when we do start to cover the one-way independent ANOVA and the one-way repeated ANOVA, much of that will be review because you've already learned most of what you need to know about them in the lab. But the first part that we're going to cover today is new. All right. So let's compare and contrast the t-tests with single factor ANOVAs. All right, so we've already said that one way, which means single factor, independent variable and factor mean the same thing, okay? So one way single factor ANOVAs are used when you have one independent variable with 3 or more levels. So now we have to ask the question, well, why can't we just compare those 3 means? Let's just use a very simple example here. So the factor has to have 3 or more, so we're just going to look at the case where there's 3 means. Why can't we just use multiple t-tests to compare the means 2 at a time, and then we'll have our answer. We'll know which means are different from which. So in other words, why can't we do this? Right, so here's your mean for level 1 of your factor, level 2, and level 3. So you have your 3 means. Why can't you just use a t-test to compare mean 1 and 2? And that t-test would tell you if these 2 means are different. And then run another t-test to see if these 2 means are different. And then finally run a third test to compare these 2 means. By the time you're done with all of that, you will have your answer. You'll know exactly which means are different from which. Now, this means that you would need to do 3 separate t-tests. And you might not think that that's a bad thing, right? T-tests are pretty easy to do on SPSS. However, each t-test here carries a risk of making a type 1 error. So if we run 3 of these, then we are inflating the total risk of a type 1 error, right? So the total alpha for all comparisons combined would exceed whatever we wanted alpha to be set at. So if we want to set alpha at 0.05, it means that we're setting it at 0.05 for each individual t-test. But by the time we've done 3 t-tests, the total risk of making a type 1 error, the total probability is going to exceed that 0.05 level. All right? And in fact, the more means you are comparing, the more t-tests you're going to need. And that means that you're going to inflate your risk of a type 1 error, the total risk, even more. All right? So it just gets worse and worse and worse. Now, a bit of terminology here. When we talk about the per comparison alpha, we're talking about the risk of making a type 1 error for every specific comparison. So for example, the t-test that is going to compare mean 1 and mean 2, we set that alpha at 0.05. That would be the per comparison alpha. Okay, so for that specific t-test comparing those two means. You would have another per comparison alpha to compare means 1 and 3, because that's a separate t-test. All right, so each of those per comparison alphas carries a risk of making a type 1 error, and what that risk is depends on what we set alpha at. If we set it at 0.05, then each per comparison alpha is 0.05. If we set it at 0.01, well, then it's 0.01. Now, the family-wise, joint, or experiment-wise alpha is the total risk of making a type 1 error for all the comparisons combined. So in other words, in the example that we've been using, for all 3 t-tests, if we were to figure out the total risk of a type 1 error, that would be called the family-wise, joint, or experiment-wise alpha. And yes, I know it's frustrating. We have 3 terms for the same thing, but that's the way it is. Okay, so you might think that all we have to do to figure out the family-wise alpha would be to just add 0.05 for the first t-test, 0.05 for the second, and 0.05 for the third. But then that means that it's just a simple addition, and that's not quite the way it works. So your total risk would not equal 0.15. All right, it's going to be less than that, but I'm not going to go into details about actually how we might calculate it. It's not really important because we have a solution, all right, to this problem. And the solution is do the ANOVA. If you do a one-way ANOVA on your data, whatever you set 0.05 to be, it's going to be 0.05 no matter how many means are being compared by that ANOVA. All right, so regardless of whether you have 3, 4, 5, 6 means that you're comparing, if you set your alpha to be 0.05, the risk of making a type 1 error will not exceed that. All right. Whereas, of course, it would if these were if you were running multiple t-tests. Every t-test you add, you're going to inflate the family-wise, joint, or experiment-wise alpha. All right. And the family-wise alpha is the same, right? Here it says joint alpha, but remember, family-wise is just another name for that. The family-wise alpha remains the same regardless of how many means are being compared.